Firstly, I'm Manikmar Pradhan, bearing roll number 18NS0006. Would like to give a big thanks to our Department of Physics and Dr. C.P. Khatiwara sir of Namji Government College and Sikkim University to provide us such a great platform to make a video on stack effect and Kerr effect for the partial fulfillment of BSc. Firstly, to know the stack effect, we should know about the hydrogen spectrum. So here we have the diagram of hydrogen spectrum, in which we can see that here we see the diagram of energy level diagram of hydrogen spectrum, in which we see that different series of hydrogen spectrum. If we get transition from higher energy level to the first energy level, it is called Lyman series. If we get transition from higher energy level to the second energy level, it is called Balmer series. If we get transition from higher energy level to the third energy level, so it is called Paschen series, and so on. Stark chose the Balmer series to observe the Stark effect, in which we get transition from energy state n is equals to 3 to n is equals to 2. We named it after H alpha line. If we get transition from energy state n is equals to 4 to n is equals to 2, we named it after H beta line. And if we get transition from n is equals to 5 to n is equals to 2, we named it after H gamma line. If we observe this Balmer series from high resolution spectrograph, further it gives 5 different component line split, and which is called fine structure splitting. If we focus this alpha line, it will split into 5 components without any external electric field. To get an idea or to understand more about Stark effect, we should know this basic thing about the hydrogen spectral line. And from hydrogen spectral line, Stark chose the Balmer series to observe the Stark effect, especially the H alpha line. Previous we studied about the basic thing which we need to understand the Stark effect. So now we discuss about the basic history. So this Stark effect is named after the German physicist whose name is John Stark, who discovered this Stark effect in 1913. This discovery of this effect, which is contributed more importantly to the development of the quantum theory. So he was rewarded a Nobel Prize in Physics in the year of 1919. So he has been inspired by the Zeeman effect to do this experiment. Initially, by doing this experiment, he faced much more failure, but later on he undertook a measurement on excited state of hydrogen atom, and he succeeded in observing the splittings of hydrogen atom into the different component. So by the use of old Bohr-Sommerfeld theory, quantum theory and all, he able to derive the equation for the linear and quadratic Stark effect of the hydrogen. Now in introduction part, we discuss about what actually a Stark effect is. It's a phenomenon of shifting and splitting. It is the phenomenon of shifting and splitting of spectral line of an atom's molecules into the number of component lined by the action of external field. That means this star effect is the phenomenon which splits the spectral line, which splits this spectral line of some atoms or the molecules into the different number of component line by the action of external field. So in this electric field, analog to Zeeman effect. That means it is this Stark effect similar to the Zeeman effect, in which Zeeman effect says that this spectral line, it splits into several components due to presence of magnetic field. But in Stark effect, we discuss about the external, by the action of external electric field, it spectral line splits into different component. So in particular, Stark effect is responsible for the broadening. That means to increase the thickness of the Stark spectral line by the charged particle. For most spectral line, the Stark effect is either linear, that means which is proportional to the applied electric field, or quadratic with high accuracy. So this effect can observe for the both emission and absorption of the line. We shall see some features of Stark effect. So every line splits into several component line. The number of Stark line increases with increase in series of parent line. The H beta line shows more effect than H gamma alpha line, and H gamma line shows more effect than the H beta line. So in Balmer series, we see that every line is split into several components. See, every line splits into several components. That means if we get transition from n is equals to 5 to n is equals to 2, it gives the H gamma line. If we get transition from n is equals to 4 to n is equals to 2, we get n as beta line. If we get transition from n is equals to 3 to n is equals to 2, we get as alpha line. So it splits into several component line. So the number of stack line increases. That means the number of stack line increases by the increase series number of parent line. That means if we get transition from n is equals to 5 to n is equals to 2, then stack line increase as compared to the as beta line. So as beta line has more stack, as beta spectral line has more stacked line than the as alpha line. So in second point, if we observe the Balmer series in applied external electric field which is parallel to the applied electric field, then we see that sigma component are unpolarized and the pi component are absent. If we observe the Balmer series by applying external electric field which is perpendicular to the electric field, both sigma and pi component are linearly polarized. So in fourth number, the component lies symmetrically on the both sides of the original line. That means in left side we have sigma component, in right side we have pi component. So if we see the splitting component line, it lie between symmetrically, means it gives the definite pattern of the spectral line. If we see that the separation between component line increasing linearly with applied electric field of 10 to the power 5 volt per centimeter, which means the separation between these two component line increase linearly when we applied electric field up to 10 to the power 5 volt per centimeter. If then it is called strong field. If we applied electric field more than 10 to the power 5 volt per centimeter, then we call this as a strong field type. So we know that the Stark effect has two types: first order Stark effect and second order Stark effect. In first order Stark effect, we see that the Stark splitting is directly proportional to the applied electric field, which means the splitting of that spectral line which is directly proportional to the applied electric field, and then this is called first order effect, Stark effect. Here spectral line are split it into component which lies symmetrically about original line which is linear. That means it gives the definite pattern of the spectral line, and further when it splits into different component, then it gives the definite pattern. Now the Stark effect, we see that if the Stark splitting is not directly proportional to the applied electric field, that means the splitting of Stark effect is not directly proportional to the applied electric field, then it is called second order Stark effect. So here spectral lines are split into component which does not lie symmetrical. That means it does not give the definite pattern of the spectral line about the original axis, but this effect is observed when strength of applied electric field is greater than 10 to the power 5 volt per centimeter. As we discussed earlier, that if we put the electric field greater than 10 to the power 5 10 to the power 5 volt per centimeter, then we get the strong electric. So I'll discuss about the weak field Stark effect. There is a weak field when Stark splitting is small compared with the fine structure splitting. That means if there exists a weak field in Stark effect, then the Stark splitting is small as compared with the fine structure splitting. That means those component which further divided in another component. So to know more about the weak field Stark effect, we should know about this diagram, which is vector model for the weak field Stark effect as well as strong field Stark effect of the hydrogen atom. That means this vector model diagram is applicable for both weak field Stark effect, and we shall discuss next in strong field Stark effect. In this diagram, I already wrote this notation: E is equals to electron, L star is orbital angular momentum, S star is spin angular momentum, J star is total angular momentum, E and E is applied electric field. So if we see in diagram, we see the electron, in which electron has two angular momentum, that is, one is orbital angular momentum and another one is spin angular momentum. So this electron is placed in applied electric field. It gives the two angular momentum, that is orbital angular momentum and spin angular momentum. By the resultant of these two angular momentum, it gives the final angular momentum, that is total angular momentum, which is projection to mj. So if we applied electric field E, if we applied electric field which is weak interaction energy between total angular momentum and the applied electric field E vector, which is considerably less than the magnetic interaction energy between total angular momentum and applied electric field is less than the magnetic interaction between spin angular momentum and orbital angular momentum, in which electric field, the spinning of electron which does not interact with the electric field E, and the coupling of this total angular momentum with the electric field E is only due to the interaction of this orbital angular momentum with electric field E. The resultant, the angular momentum precise only around the applied electric field it with projection mj, and the value of projection is plus j2 minus j minus 1 to minus j. Already studied that Stark effect means the splitting of spectral line into the several different components by the external electric field. So this is, if we want to see the splitting, so we can see with the help of energy level diagram of that atom. As an example, we shall take H alpha line of Balmer series. H alpha line of Balmer series we take as an example. As a H produce when it get transition from any energy state n is equals to 3 to n is equals to 2. So this transition, so we produce H alpha line. So if energy state n is equals to 2, then L is equals to 0 or 1 and spin is half. So if we take L is equals to 0, then S is equals to, we get half, and J is equals to half. That means J is equals to plus minus L plus minus S. So we get 2S half. That means this is the notation of energy level. So to draw the energy level diagram, we should know the notation first of that energy level. So H alpha line to produce the notation of the energy level. So similarly, if we take L is equals to 1, so spin is as always half, then J is equals to 3 by 2 and 1 by 2. So it gives 2p half and 2p 3 by 2. So for energy state n is equals to 3, so if we take L is equals to 0, then spin is half, J is equals to half. So we get 2s half. So if we take L is equals to 2, spin is half, J is equals to 3 by 2 and half. So we get 2p 3 by 2 and 2p 3 by 2. So if we take L is equals to 2 and S is equal to half, we get J is equals to 5 by 2 and 3 by 2. So here energy level notation we get 2d 5 by 2 and 3d 3 by 2. So this energy level notation we get from if L is equals to 0, then we take as subcell. If L is equals to 1, we take as P cell. If L is equals to 2, we take a D cell, and if L is equals to 3, we take as an F cell. So we segregate this energy level into two pairs. That means degenerate energy level and unpaired energy level. If we get the degenerate energy level, then it further splits into furthermore component, which is the phenomenon of the Stark effect, Then if unpaired energy level is there, then it will not further divide into furthermore component. So for energy state n is equals to 2, the degenerate energy level is 2s half and 2p half, and unpaired is 2p 3 by 2. The state n is equals to 3, the degenerate energy level is 3s half or 3 to half and 3 to 2p 3 by 2 and 3 2d 3 by 2. So unpaired energy level is 3 2d 5 by 2. So how we can get degenerate energy level is from that. If the value of n is equals to j, then we found the degenerate energy level, which is furthermore splitted into furthermore component, and this is what I called the phenomenon of the Stark effect. So previous we discussed about the energy notation of H alpha line in from Balmer series to know the further it splits into different component or not. So energy label notation, that is, this is unpaired energy label from energy state n is equals to 3 2d 5 by 2, and we get two degenerate energy level, that is 3 by 2 and 3 3 by 2, 3 s half and 3 p half. This is from energy state n is equals to 3 when we didn't apply any field, that is there is no field while having this transition. So if we see in energy state n is equals to 2, we get 2p 3 by 2, which is unpaired, and 2s half and 2p half is a degenerate energy level. Further it splits into furthermore component, which is the phenomenon of the Stark effect. So give the transition, we should know about the selection rule, which is delta j equals to plus minus 1 selection rule. So if we get transition from the 2s half 2p half, it will get transition up to 2p 3 by 2. It allows the selection rule and it gives the 5 transition. So we see that if there is no electric, if we haven't applied any field, then it gives the 5 transition. If we applied small electric field, that is up to 10 to the power 5 volt per centimeter, it is up to 10 to the power 5 volt per centimeter. If we apply this electric field, then energy level it will not further split, so it goes up there, and these two right line are further splitted into further component, and it gives the Stark phenomenon. So it is split into 4 energy level. That means the value of mj is equals to plus minus j. That means the value of j is 3 by 2. So plus minus j up to minus j, that means plus 3 by 2 half minus half and minus 3 by 2, it's up to plus 3 by 2 to minus 3 by 2, and its energy level is 4. So and this s half and 2p half also furthermore split it into further component, so it has two energy level, plus half plus minus half, and here also plus minus half. So and in energy state n is equals to 2, this s half and 2p half furthermore split it into two component, that is plus minus half and plus minus half. This how we get the value of mj is equals to plus minus of j. We know the value of j is this, which is below the subcell number. So if we apply it up to 10 to the power 5 volt per centimeter, that is like weak field, this first line will not take part in transition, means it will not further split it into more component, so it will goes on like this. So if we get transition from s half to 2p half, then we get transition up to here. So by seeing this diagram, you all know that I will get transit from different energy level to means high energy level to the lower energy level. So it follows the selection rule. For mostly it follows the selection rule. So here we see that if we apply the 10 to the power 5 volt per centimeter electric field up to here, not more than that, up to this electric field, if we apply this electric field, then we get 5 several different component spectral line, which furthermore split from this energy level. This 3 energy level gives the furthermore splitting component line. So by the external electric field up to 10 to the power 5 volt per centimeter, it will give the furthermore 5 transition component line, which is the Stark effect phenomenon. We come in strong field Stark effect. Strong field Stark effect is said to be strong when splitting of energy level is greater than the fine structure. That means the electric field is to be strong when splitting of energy level. That means when energy level splits into different energy level, then it is greater than the fine structure. That means it further divide into several component but more than weak field. We get 5 several component, splitting component in weak field, but in strong field we get more than 5 splitting several component line. So as we discuss in strong weak field Stark effect, this diagram, in this diagram we discuss about this applied electric field. This is vector model of hydrogen atom. So this diagram is applicable for this strong field Stark effect too. A strong field for hydrogen is for which interaction energy between total angular momentum, that is the interaction energy between total angular momentum, that is J star, and to the applied electric field E vector is much more greater than the magnetically interaction between orbital angular momentum L star and the spin angular momentum S star. A strong electric field hydrogen is for which the interaction energy between the total angular momentum J star and the electric field is greater than the magnetic interaction energy between L star and S star. That means this orbital angular momentum and the spin angular momentum. That means the magnetic interaction between these two angular momentum is greater than the total angular momentum, and the electric field, applied electric field, for which Stark splitting energy due to field is greater than the fine structure splitting. As we discussed here, that if electric field is strong, then the energy level is greater than the fine structure splitting. It is a strong field. That means it is the strong field for which first order Stark effect is observed. So Stark effect, we should draw the energy level diagram for the H alpha line of Balmer series, which get transition from n is equals to 3 to n is equals to 2. So for energy level diagram for the Stark effect, this table to make energy level diagram for the H alpha spectral line of the Balmer series, we get transition equals to 3 to n is equals to 2. So energy state n is equals to 2 and n is equals to 3. This n1 and n2 is nothing but it is the parabolic quantum number. So n is equals to 2, then we get this parabolic quantum number 11100100. So if we doing mathematically, and n2 minus n1 and n2 minus n1, then this is the electric quantum number. That means ml is the electric quantum number. So in this energy label we found how many? We found 2, means here 0 minus 1 and 1, means all the others are repeated, right? 0 is repeated. Here we found minus 2, 0 and 2, others are repeated. So n is equals to 3 means energy state 3 मा हेर्नु पर्दाखेरि चाहिँ what we found that parabolic quantum number we found 9, right? So if n n1 and n2 are 2 2 2 1 like this, if we can see that in this table. So if we calculate this n2 minus n1, we found that n2 minus n1, that means 2 minus 2 is 0, 2 minus 1 is 1, 2 minus 0 is 2. That means we can see in this table is minus 2 minus 1, it means 0 minus 1 or 2. That means we get 5 energy level. Here also we get minus 6 minus 3 0 3 6. Here also we get 3 energy level. That means 5 transition level. So according to this table, we can make the energy level diagram for the strong field effect. Strong field Stark splitting of the H alpha line, in which we see that the n2 minus n1 is nothing but n2 minus n1 for n is equals to 3 minus 2 minus 1 0 1 2. That means minus 2 minus 1 0 1 2. Others are not necessary because it is repeated once or twice. So if n2 minus 1 for the n is equals to 3, it also 5 transition line. So in n is equals to 2, it gives 3 transition line. That means 0 minus 1 1 and minus 2 0 2. So the transition from higher energy level to the lower energy level, that means by the using of selection, by using the selection rule, we found this transition lower and higher to lower, which splits into further 15 more component line. That means more splits into 5 component, and if we in strong field effect, this line splits into 15 more component line. So this also allow the stack phenomenon. We know that there is two component. First one is pi component and second one is sigma component. So this upper line, this upper case is considered as a pi component. The lower case is considered as a sigma component. Application of the Stark effect, in which it explains the theory of molecular formation of atoms. It also explains the broadening of the spectral line. That means it increases the thickness of the spectral line. It also helps to explain the thickness of the spectral line. It also explains the dielectric constant. It also used to describe the effect of the time dependent electric field. Now the another topic is Kerr effect. So, Kerr effect, it is the phenomenon in which a non-linear optical effect which can occur when light propagates in crystal and glasses, but also the gases. It can be described as a change in refractive index caused by electric field and being proportional to the square of electric strength non-linearly. It is also called as quadratic electro-optic effect. All materials show a Kerr effect, but certain liquid display it more strongly than others. That means it is the phenomenon in which a non-linear optical effect, that means input is not directly proportional to output. That is, it is a non-linear optical effect which occur when light passes through a crystal or a glasses, or in some cases gases too. Changes of refractive index caused by the electric field which is being proportional to the square of applied electric field which is non-linearly. This is called Kerr effect. Mathematically, we can show that the change in refractive index, that means change in refractive index is directly proportional to the square of the applied electric field, and change in refractive index is equals to some Kerr constant and applied electric field E square. Basic history, we see that this Kerr effect was discovered in 1875 by John Kerr, a Scottish physicist. These two special cases are normally considered in Kerr effect, that is Kerr electro-optic effect, which also called DC Kerr effect, and optical Kerr effect, which is also called this AC Kerr effect. It comes under the category of non-linearity. The setup for the Kerr effect. So, with reference to the special cases, the Kerr effect is further divided into two parts. That means electro-Kerr effect, electro-optic Kerr effect, and optical Kerr effect. So, in Kerr electro-optic effect, or it is also called DC Kerr effect, it is a special case in which slowly varying external electric field is applied. Means it is slowly external electric field is applied to a non-linear medium which influence the sample becomes birefringent. That means it acts as a polarized which is perpendicular to the applied electric field. That means birefringent with different indices of refraction, with different refractive index of the light polarized or perpendicular to the applied electric field. The difference in index of refraction, which is delta n, is given by delta n lambda k E square, where lambda is the wavelength of length, k is a Kerr constant, and E is the applied electric field. Is the difference in index of refraction, that means the change in refractive index cause the material to act like a wave plate. That means wave plate is the optical device that alters the polarization state of light wave traveling through it. Behaves like a wave plate when light is incident on it in a direction perpendicular to the electric field. Higher the value of Kerr constant allow complete transmission to be achieved with smaller applied electric field. This means if the value of Kerr constant is high, then it allows the complete transmission to be achieved in a small amount of electric field. Then to the Kerr constant, if the Kerr constant is high, then it will give the complete transmission. So some polar liquids such as nitrotoluene, nitrobenzene exhibits larger Kerr effect constant. Optical Kerr effect, or it is also called as AC Kerr effect. AC Kerr effect, in which it is more prominent liquid. In this case, electric field is due to light itself. That means when we apply that, this electric field act itself as a light, and this causes the variation of refractive index, which is proportional to the local irradiance. That means which is proportional to the local irradiance power which is received by the surface unit area, that is called irradiance of the light. This refractive index variation is responsible for non-linearity optical effect of self-focusing. That means this refractive index variation is responsible for the linearity. It's something which is input directly not proportional to the output, and non-linear optical effect of self-focusing. Self-focusing is a non-linear optical process induced by the change in refractive index of the material. And self-phase modulation. It is also a non-linear optical effect of light matter interaction and modulation in stability. It is the phenomenon where deviation from periodic waveform are reinforced by non-linearity, leading to the generation of spectral side band. If we pass light from the laser, then it will become more significant. This magneto-optic Kerr effect, it is the phenomenon in which it exhibits a slightly rotated plane, that means slightly rotated plane of polarization when reflected from magnetized material. One demerit is that it is weaker compared to focal effect, in which changes in refractive index varying linearly to the value of applied electric field. It has application. So it has been applied to digital photography to create a type of shutter with very short exposures and rapid reaction. It also used for waveguide and spectroscopy of the liquid.